In this lecture, we're going to discuss another classical algorithm called the bully algorithm. In the bully algorithm, all the processes know the other processes' IDs, and when a process finds that the coordinator or the leader has failed, it can find this via the failure detector. If the process knows that it is the process with the next highest ID after the leader, it elects itself as the new leader, and it sends a coordinator message to all the processes that have lower identifiers than itself. At this point, the election is completed. This is why this is called a bully algorithm. Essentially, if you know that the bully has crashed the highest ID process and that you're the next highest ID process, then you become the new bully and you tell everyone else with a lower ID that in fact you are the new leader and the new bully in the system. However, if you know that you are not the next highest ID process in the system, then you can't be the bully. You initiate an election by sending an election message. Whom do you send an election message to? You send election messages to only those processes that have a higher ID than yourself. Essentially, you're trying to ask these processes, hey, are you guys still alive? Are you guys willing to be the leader, or should I become the new leader? If none of these processes responds within a timeout, then this initiator becomes a new leader by becoming the bully, and it sends a coordinator message to all lower ID processes. At this point, the election is completed. However, if an answer is received within a timeout called an OK message, then there is some non-faulty process with a higher ID, and so this process needs to wait for the coordinator message. Once again, if it does not receive a coordinator message within a timeout, it starts a new election run. What does the process do when it receives an election message? Now, remember that an election message is always received from a lower ID process. When an election message is received from a lower ID process, essentially the lower ID process is saying, hey, the leader has crashed. Here's a new election run being started. Should I be the new leader? And you need to tell the lower ID process, you need to bully the lower ID process into not becoming the leader by sending it an OK message. An OK message would suppress the lower ID initiator, and it would make it wait for you. When you receive an election message, if this is the first election message you're seeing, you would need to start your own leader election by sending election messages to processes that have a higher ID than you. And the protocol continues until the highest ID process is elected as the leader. So let's see an example of this. Again, we have a system of 6 processes. N80 was the old leader, it crashed, and say N6 is the lucky one in the group who has detected the failure of N80. What it does is that it realizes that it is not the next highest ID process in the group, and so it needs to send an election message to all the processes that have higher ID than itself, which are essentially N80, the failed process. Yes, it does send a message to the failed process as well. It sends an election message to N32 and also to N12. When N32 and N12 receive these messages, they know that they are in fact alive, and so they send back an OK message to N6, which then waits for the final coordinator message. In turn, N12 and N32 also start election messages of their own by sending election messages to their higher ID processes. So N12 sends election messages to N32 and to N80, and N32 sends an election message to N80. When N32 receives N12's election message, it sends back an OK, and this suppresses N12 and makes it wait. N32 would time out waiting for N80's reply, because N80 after all has failed, and it would now know that it is the new leader. It then sends a coordinator message to all the lower ID processes in the system, which essentially is all the other processes that are alive in the system, and at this point of time the election is completed. N32 is a new leader, and everyone else knows about this leader. So you could also have failures that happen during the election run. So N32 might fail after it has sent the election message, but before it sends the coordinator message. And at this point of time, N12 and N6 need to do something about it. Right? So essentially what happens is that N6 or N12 would time out waiting for N32's response, and then it would start a new election run, which would send a message to N12, which would then start another election run by itself, and eventually N12 would get elected as a new leader in this particular case. If N12 also were to fail, then N6 would also time out waiting for N12's reply after N12's OK message, and then it would start the new election, and then it would time out, and then it would finally become the leader in the group. So if failures stop in the system, eventually you do elect a leader, but if failures keep happening, then you may never ever elect a leader. But how do you set these timeouts? How long do processes wait? Well, how long processes wait really depends on the worst case time to complete election. The worst case time turns out to be 5 message transmission times if there are no failures during the run. And you can set your timeout to be this. Why is it 5 message transmission times? Well,
Consider the worst case, which happens if the election is started from the lowest ID server in the group. So the lowest ID process in the group initiates leader election. Once it sends the election messages out, it receives OK messages. So the answer that the lowest ID initiator gets from the second highest ID process, the would-be leader, takes another message transmission time. So that's step 2. Next, you have the election message from the second highest ID server that goes out to the highest ID process, which is in fact the failed leader. That's the third message transmission time. Then the second highest ID process waits for the highest ID process to respond, and there's a timeout for that as well. That's the fourth message transmission time. And then finally, when the second highest ID process realizes that it in fact is the new leader, it then sends a coordinator message to everyone. That's another message transmission time. Those who have looked at this for a while may realize that the steps 2 and 3 can in fact be commingled and done parallelly, where you can send OK messages to the lower ID processes alongside and parallelly with the election message that you send to the higher ID processes. And so in fact you can reduce this to be just 4 message transmission times if you so wish. So the worst case completion time is 5 message transmission times. That determines the timeout. What about the number of messages that are sent during this worst case? The worst case happens when the process with the lowest ID in the system detects a failure. It sends election messages to all its higher ID processes, and all the n-1 processes in the system start an election protocol by themselves. Right? So this means that the number of election messages sent out by the ith highest ID process is I-1. And so you have a total number of election messages in the system that is equal to n-1 plus n-2 plus so on and so forth, all the way plus 1. Okay, there's a number of OK messages that is equal to each value of this minus 1, because the highest ID failed leader does not respond. But essentially, the number of total messages is order of this value. This turns out to be n-1 times n divided by 2, which is order n squared. So the worst case message complexity is fairly bad. It's quadratic, but at least you have a short turnaround time for the protocol to complete. Well, that's the worst case. What about the best case? The best case happens when the second highest ID process in fact is the one that detects a leader failure. It immediately knows that it is the next highest ID process in the group and is a new leader. It simply sends out coordinator messages to the remaining n-2 processes with a lower ID than itself, and so the completion time is just 1 message transmission time, and the total number of messages involved is n-2 messages. So what about the impossibility here? It seems like this protocol might actually solve a consensus. However, since timeouts are built into the protocol itself, this means that the protocol may never terminate because liveness is not guaranteed. But it doesn't guarantee liveness in the asynchronous system where the message delays may be unpredictable and processes may be arbitrarily slow. However, in the synchronous system model, where processes have a maximum time to take an instruction a step, and there is a maximum upper bound on how long a message takes to be transmitted, you can actually calculate the worst case one-way latency as the worst case processing time for the instructions plus the worst case one-way message latency. Using these, you can set your timeouts to be the worst case values, and in fact you can guarantee liveness in this way in the synchronous system using the bully election protocol. To wrap up our discussion of leader election, election is an important component of many cloud computing systems today. We have discussed 2 classical leader election protocols, ring-based and bully, but they are failure prone because after all, leader election is related to consensus, which turns out to be impossible to solve in an asynchronous system. Many systems in industries such as Google Chubby as well as Apache Zookeeper, which is an open source system, use Paxos-like approaches or quorum-like approaches in order to do elections, which guarantee safety. They may not guarantee liveness, but they guarantee eventual liveness. If things go right in the system in terms of message losses and failures, then the election succeeds and everyone knows about the unique leader that is elected in the group.